The AIM-9 Sidewinder is one of the most famous and widely used anti-air missiles in modern aviation history. Born in the late 1940s as a simple heat-seeking weapon and continuously evolved through dozens of upgraded variants, the Sidewinder has become a benchmark for short-range, infrared-guided missiles. In this review we'll explore its outward design, the interior systems that make it smart, its performance envelope, operational use, and how cost and procurement shape its role on today's battlefields, all from the perspective of a technical deep dive but told in a natural, viewer-friendly narrative. At a glance, the Sidewinder looks compact and purposeful. It's typically about 2.9 to 3.7 meters long depending on the variant, with a slender cylindrical body, stabilizing fins near the mid-body and tail, and a conical seeker head at the nose. The airframe is engineered for aerodynamic stability at high subsonic and supersonic speeds. The fins provide lift and agile maneuverability while control actuators precisely vector the missile in flight. The missile's exterior is rugged and utilitarian, heat-resistant coatings where needed, access panels for maintenance, and standardized mounting points so it can hang on a wide range of aircraft pylons and launch rails. Colors vary by operator and variant, many are in neutral gray or olive drab to match military schemes, but the functional design language is the same: minimal ornamentation, maximum survivability in high-G launches, and high-speed intercepts. The nose houses the seeker dome, one of the defining elements of a Sidewinder. Early models used a simple infrared (IR) seeker that locked on a hot exhaust plume and guided the missile toward that source. Over decades the seeker evolved dramatically. Modern seekers are imaging infrared (IAR) or advanced focal plane array sensors with cooling and onboard signal processing, capable of discriminating targets, resisting flares and countermeasures, and even acquiring targets against complex backgrounds like the sun or ground clutter. The seeker is typically cryogenically cooled to reduce sensor noise and increase sensitivity to faint infrared signatures, a process made reliable through decades of engineering improvements. Behind the seeker sits the guidance and control electronics, microprocessors, inertial sensors, and often a data link interface. These components fuse seeker data with inertial and, where applicable, data link updates from the launching aircraft. Modern Sidewinders can receive mid-course updates, allowing the launch aircraft or another platform to refine the target location after launch. The missile's flight computer processes guidance laws, often proportional navigation or its advanced variants, to compute steering commands that the actuator system implements. Redundancy and electromagnetic shielding are engineered into this compartment to ensure survivability against electronic warfare and the mechanical shocks of launch. The warhead and fusing mechanism occupy the mid-body. Sidewinder warheads are relatively compact but optimized for lethality, typically an annular blast fragmentation charge designed to rupture aircraft structures and damage vital components. Proximity fuses, usually active radar, laser, or centimeter-wave sensors, allow the missile to detonate at the optimal point, maximizing kill probability even when a direct hit isn't achieved. Some variants also include directional fragmentation patterns or focused blast geometries to increase effectiveness against different target types. Safety interlocks and arming delays keep the device safe until clear flight conditions are met during launch. Propulsion is in the rear section, a solid-fuel rocket motor that burns a composite propellant optimized for rapid acceleration and high-thrust pulses. Designers balance burn profile, impulse, and grain geometry to manage acceleration loads and trajectory shaping. Advanced variants have motors with smokeless propellants or enhanced performance grains that extend range and increase top speed, while some experimental efforts have looked at two-pulse motors or throttleable designs to shape mid-course trajectory. The exhaust plume design and nozzle geometry are tuned for efficiency across launch altitudes and speeds, and the entire propulsion unit is constructed to resist thermal and mechanical stress. Inside the missile, the architecture is a concentrated example of modern compact engineering: sensors, processors, power sources, and actuators packed into a few meters yet designed to function under tens of Gs of launch acceleration. The power source is usually thermal batteries or advanced reserve batteries that remain inert until launch and then provide reliable power for the seeker, processors, and actuators. Cabling and connections are vibration-hardened. Components are shock-mounted on elastomer cushions to survive the violent dynamics of a rocket launch. Cooling for the seeker, EMI shielding, and thermal management systems are critical internal subsystems that allow the missile to operate in extreme temperature environments, from high-altitude cold to the heat of supersonic flight. Performance-wise, the Sidewinder family spans a wide envelope depending on the block or variant. Early AIM-9s were designed for short-range engagements, think visual range dogfights, with ranges of a few kilometers and speeds around Mach 2 to Mach 2.5. Modern versions, such as the AIM-9X and its follow-ons, extend range, agility, and countermeasure resistance significantly. AIM-9X Block 2 and Block 3 models have off-bore sight capability coupled with helmet-mounted sights, enabling pilots to cue a lock simply by looking at a target and launch a missile at large angles relative to the aircraft's nose. This look-and-shoot capability radically changed short-range air combat tactics. Flight performance often reaches transonic to supersonic speeds with maneuvering loads well above 5. Launching platforms are varied and global. The Sidewinder is carried by fighters and attack aircraft from many nations, F-16s, F divided by a -18s, F-15s, Eurofighter Typhoons, Mirage series, various MiG and Sukhoi derivatives in countries that license or buy Western weapons, helicopters, and even some ground-launched and naval adaptations. Its adaptability to pylons, rails, and different launch interfaces is a design strength. The missile's separation dynamics are predictable and well characterized, allowing safe carriage inside weapon bays or externally under pylons. Tactically, Sidewinders have influenced aerial combat doctrine. The missile's combination of speed, agility, and fire-and-forget guidance supports both defensive and offensive tactics. The integration with helmet-mounted cueing gives pilots unprecedented situational responsiveness. A pilot spotting a threat in peripheral vision can rapidly acquire and destroy it without pointing the aircraft directly. Modern rules of engagement often combine sensor fusion from aircraft radars, infrared search and track systems, and data links to present a composite tactical picture that maximizes the effective employment of short-range missiles like the AIM-9 family. Historically, the Sidewinder has a storied combat record with engagements spanning decades. Its successes, and lessons learned from limitations, shaped Air Force's procurement and upgrade strategies. The missile has been continuously produced and modernized so that legacy airframes benefit from upgraded weapons without needing complete platform replacements. That service life extension and modular upgrade path keep the missile relevant and cost-effective. Speaking of cost, price is a complex topic because it depends on variant, production lot, integration configuration, and buyer. Roughly speaking, older basic Sidewinder variants are relatively inexpensive by modern standards, tens of thousands of dollars apiece in earlier decades. Contemporary advanced variants like the AIM-9X Block 2/3 are more expensive due to advanced seekers, processors, and data link capabilities. Prices per round can sit in the low to mid six figures, subject to contract terms, quantity discounts, and support packages. Governments purchasing missile packages usually negotiate lifecycle support, spare components, training, and integration work into the contract. Acquisition cost is only a portion of true program expense. When comparing cost-effectiveness, Sidewinders provide a favorable balance, relatively modest per round cost versus high probability of mission success in short-range air combat. Maintenance, storage, and logistics are additional cost drivers. Missiles require periodic inspections, shelf life management for batteries and propellant elements, and software updates to keep guidance algorithms current. Many customers opt for block upgrades that retrofit older missiles with modern seekers or processors rather than buying entirely new rounds, and economic. Variants are central to understanding the system. The original AIM-9B/C types were early heat seekers with limited countermeasure capability. The AIM-9L in the late 1970s introduced all-aspect capability, allowing engagement from the front rather than only from the rear. The AIM-9M improved resistance to flares and electronic interference. The AIM-9X series represents a leap, imaging infrared seekers, high off-bore sight capability, thrust vectoring control on some models, and data linking to allow mid-course updates and target handoff. Export variants and licensed builds have proliferated globally, each adapted to local integration needs and aircraft fleets. Operational employment has evolved as well. In modern conflicts, the missile is used not only in traditional air-to-air roles but also in some surface-to-air adaptations and tests for close-in defense roles. Its compact size and precision make it an attractive option where small, agile interceptors are needed. Rules of engagement in dense airspaces have made the pilot's decision cycle and missile queuing systems as important as the missile's intrinsic capability. A highly capable missile is less useful if the pilot can't detect or decide in time. Ethical and legal aspects matter too. As with any weapon system, use is governed by international law and engagement protocols designed to minimize civilian harm and collateral damage. The Sidewinder's precision guidance reduces risk of collateral damage compared to unguided weapons, supporting adherence to proportionality and discrimination principles in lawful military operations. From a design perspective, the Sidewinder family exemplifies evolutionary engineering. Iterative improvements in sensors, software, and control actuators have kept a mid-20th century concept at the cutting edge of 21st century air combat. It also highlights industrial advantages of a modular approach. Standardized airframes and interfaces allow multiple generations of seekers and electronics to be retrofitted, preserving investment in existing stocks and simplifying aircraft integration. Looking forward, future iterations of short-range air-to-air missiles will continue to emphasize imaging sensors, artificial intelligence-assisted target recognition, networked engagement where multiple platforms coordinate missile employment, and propulsion improvements for even greater kinematic performance. Efforts to improve countermeasure resilience, to fuse multispectral seeker inputs, e.g., infrared plus millimeter wave, and to incorporate more sophisticated target prioritization logic are logical directions. The Sidewinder lineage, with its proven baseline and upgrade path, is well positioned to absorb and demonstrate many of these technologies. In sum, the AIM-9 Sidewinder is more than an artifact of aviation history. It is a living family of systems that continues to define short-range aerial combat. Externally compact and resilient, internally sophisticated.